B, corrected this mistake for our model, and then we realized, hey, these are nasty fractions. What if we just put everything in MATLAB from now on? So I'll show you how to do this. Well, let's go over to MATLAB here, and we will start a new section for mixing problems. And let me clear all other outputs, and we'll get started. So here, the first thing I'm going to do, clear all old variables. And you do that by writing clear all. Then what we do is we define the coefficient matrix. So we'll call that A, square brackets, and we have -3 over 100 and 1 over 100 in the first row, and 1 over 50 and -1 over 25 in the second row. I don't want that to output. I'm going to define the forcing function, and I'll call it f. So f is going to be equal to 0 in the first row and 1 in the second row. Okay, so now what do I do? Well, now I'm going to find the eigenvectors and values for A. And how do you do that here in MATLAB? Well, I would first check with the eigen function if it's a repeated root or not. And then if it's not, and in this case we know it's not, we can just go ahead and use the Jordan. And the Jordan will output two things. So we'll need this type of variable name, which is a list of variables. It's going to be the vectors first and the values second. And we want it to output, so I won't put a semicolon here because we want to see that. Now what I'm going to do is I'm going to define the complementary solution, which happens by solving the homogeneous, which is basically doing this and finding the vectors and the values. And so we'll call that x sub c, and that's going to be equal to our vectors. It's going to be a linear combination of the two solutions that we get with the two eigenvectors that we get, because this is a 2 by 2. So we're going to have to multiply it by some constants, and then we're going to multiply it by vectors, which is whatever is outputted here. The first column right here for the first vector multiplied by e to the values, and that's going to be the first row first column times t, plus c2 times the same command, but we're going to change some things inside. So this is going to be the second column now outputted because it's the second eigenvector, and this is going to be the second value. And to understand this, if you press Control Enter, I'll show you what it does. Well, first of all, it tells you it doesn't recognize the variables. But this is the output of the Jordan. So the vector is -1/2 and 1. So when I say colon and 1, I'm saying the whole column, the first one, and then here, the whole column, the second one. And then I'm pairing them up with this is a 2 by 2 matrix, see? So the first row, first column is going to be this eigenvalue. And I'm going to put it right here as the coefficient of the t, which is the exponent of the e. And I do the same here for this entry, which is a second row, second column. So now I declare my variables, declaring my variables, and I'm going to do it by saying sims c1 and c2. And there's also a t in there. And then if I press Control Enter, we're going to get the complementary solution. Now, what they want us to do is, this is not it. They want us to guess a particular solution. And now remember that our forcing function is this. So if it's a constant, I would guess a constant vector. So let's give it some variable names to this vector, and we'll call this particular solution x sub p, and it's going to have values a, b. Now, finding a and b, we want to plug this back into the form of our system, which is the derivative of the solution is equal to the matrix A times the solution plus f. And we want to have it equal to this. And then we want to solve for A and B. And I wonder if it does it if we just do this. So A and B, close here. And so we want to rename A and B here. Let's see if it gives us an error or not. Well, it tells me, hey, you need to recognize the variables. So let's name variable A and variable B. Let's declare them. And then here we're going to get through all of this. And they're saying, hey, the dimensions are not matching. And that's because here we're supposed to have a semicolon. So let's try one more time. Let's see where this goes. It solves it. So now what we can do is we can redefine this, because MATLAB has these memorized, so it won't just put A and B, it would put the value of A and B. So redefining the particular solution. And now that we have the particular solution, we can define the general solution, which is just going to be x of t, which is the sum of x sub c of t plus x sub p. And that's going to be our general solution. So, what we can do now is we can check the solution by doing the same thing that we did up here. So we're going to say that the derivative of my solution has to be equal to a times my solution plus the forcing function. And we'll just check if it's true. So Control Enter. Here, the answer is that the left is equal to the right. So we know that this is a solution that works in general terms. Now, we need to solve for the initial conditions. So the initial conditions was that at 0, the amount of salt in tank A was 60 and the amount of salt in tank B was 10. So in other words, they're saying that 0 and 10 has to be equal to our solution when we input 0. And this can be easily put as the argument of the solve function, and we can tell it to solve this time for C1 and C2 here. We can tell it to solve for C1 and C2. We can close the argument, and then we want C1 and C2 to be renamed by the values that they find. So C1, comma, C2. And now that we get this, let me write what we're doing. So solving for C1 and C2 given initial conditions x1 of 0 equals 0 and x2 of 0 equals 10. And then I can redefine the general solution, and we actually have to rewrite this because x is now saved with the letters C1 and C2. Well, we could try and see if it changes this, but let's just do this. But now we know what C1 and C2 r, and we can say that x of t is going to be equal to this plus xp. And we press Control Enter. And here they solve for it, and it substitutes them for C1 and C2.